plus morning. Okay, in last lecture we talked about the meta material. Okay, so this is a very hot topic. Some staff in our department, some teachers also focus on this topic. This is our left-handed meta materials. So this is an interface. So here we assume that mu equal to 1, mu equal to 1 is there. Another media is mu equal to minus 1, mu equal to minus 1, mu equal to minus 1. This is that's meta material. So I think the interesting feature is the incident wave with something here. It's a reflective wave. Okay. But for meta material, it's something like this. This is for energy. Okay, energy propagation direction. But the phase is something like that. This is K direction. Okay. For physical reason, get this because of n equal to minus mu epsilon equal to minus 1. Okay. So the refract index here equal to minus 1. So the E, H, and K, they form a left-handed system. Okay, we form a left-handed system. E, H, and K. We call so this is a name for E, so meta material. Okay. So this is a very important field. Okay. But this material cannot be achieved in natural existing material. Okay. No natural existing material satisfy the relationship. So at the microwave regime, so this at a microwave regime we have two kinds of material. One is a wire, okay, metallic wire, something like this, metallic wire. This metallic wire, effective sigma. I mean, if I see this as a homogeneous material, okay, this is a homogeneous material. The effective epsilon, okay, smaller than 0. The basic idea is change the omega p, because we know that the omega, if the omega smaller than omega p, the epsilon is negative. So the omega p here is NE squared equal to epsilon E m effective. Okay. So the author just use they reduce the electron density. Okay. They reduce electron density N. Okay, and increase effective mass M. Okay. While you reduce N and effective mass, the omega p can go to the around 10 over 10 gigahertz. 10 over 9 gigahertz is microwave regime. Okay. So here, I think the very important thing is the analogy idea. I think analogy is a very important physical tools to understand things. Right? We know that it's m dx squared or dt squared plus 4 dx or dt and plus m omega 0. We call this kx. Is some f. Okay, this is a harmonic oscillator. It's a harmonic oscillator. It's a rainbow model. Okay. This is a rainbow model. It's similar L dx or dt squared plus r, sorry, dq or dt, and plus plus C over 1 and the Q equal to V. This is fully analogous. This LC circuit is R, is L, C, and V. This is analogy. So here we know that the M just equal to L, the pole, the damping of friction is R, and the P, the spring constant, just equal to 1 over C. Okay, it's fully analogy. So it's very similar to each other. So when you increase the self-inductance, they can increase the effective mass. Increase effective mass and use very sparse metallic wire, they can reduce the N. The pull them together, omega P can be down to the gigahertz. So this is why the reason they can achieve it by Pandry's idea. This is very important. This is by Feynman's book. Okay, so fully analogy. You can see that. It's everything very interesting. You can see that this is inertial, right? So when you stop a train, the people will throw out. It's really so inertial. They're very similar to L. When you cut this circuit, the inductor also keeps the current. Okay, to far below. It's very similar. This is by Feynman's book. Okay, it's fully analogy. Okay, so this is the first idea. The second idea just use a split ring. Okay, this split ring, maybe I can use this. I use this is good. Maybe I use something. Okay, this is HINC. This is H reduce. Okay, this is Lorentz shift resonator. It's a Lorentz shift resonator. Everyone know the Lorentz shift resonator. I talk about this couple theory. This is something like this. This is phase. Okay, maybe there no problem. This pile 2. This 0. This 0. This is high. Okay, this is called in phase. This is called out of phase. Out of phase. So before this is resonance frequency, they release the resonance frequency. This is resonance frequency. Omega resonance. So the before resonance, they are in phase. What's the meaning of in phase? It means this material effectively can be say a paramagnetic. It means the induced field the directional induced field is the same with the incident magnetic field. Okay, so they call in phase. Okay. But after the omega c, the outward phase, what that means the induced H field will the directional induced H field will reverse to the directional incident field. We call it outward phase. Okay, but this is effective mu. Only at this small region. Okay, this is the resonance frequency. This is the effective mu effective. Okay, this is okay. So only at this region, use another color. Only at this region, the mu is equal to. So first thing, the region should be out of phase. Another, this region should be very close to resonance. Why? First thing, they must at out of phase because induced field has a reverse direction to the incident field. Okay, so it's an out of phase region. Another, it should be very close to resonance frequency because the resonance, if around the resonance frequency, the resonance is very strong, so the induced field can be reversed to. I mean the amplitude induced field maybe can be larger than the incident field, similar to this concept. Okay, so they can flip the sign. Okay, they can flip the sign. So this is the reason. So this is the negative mu. They achieve this negative mu just due to the resonance. Okay, just due to the resonance. And this structure is non-resonance structure. This structure is non-resonance. Okay. So this is a narrow band. Okay, this region for very small band. And above is the broad band. So this is a basic idea for this achieve this negative mu and the negative MC. Okay. So in last lecture, I showed some picture. Harmonic reaction. in last lecture, I showed some standard structure in microwave. Okay, like a metallic wire. You can see an electrical dipole because it has a charge, electrical charge. Okay, here. Okay, it has an electrical dipole. Okay. Similarly, split ring. This is a loop current. It's something like this. So it's similar to a magnetic dipole. Okay. It has a complementary structure. Complementary structure. For this complementary structure, this is a magnetic dipole. This is electrical dipole. Okay. So this is by the Brownian frequency. The first experiment to realize the left-handed metamaterial just by David Smith, they use the metallic wire and the split ring together because metallic wire has effective permittivity negative, and the split ring has a magnetic effective permeability negative. Okay, so they put them together to achieve this left-handed metamaterial. This is by David Smith. You can see they put everything isotropic. You can see the orientation. This orientation along here, this orientation along here is similar to isotropic. So, in optic regime, the first pattern, in optic regime, the first successful pattern is use this parallel bar. Due to plasmonic coupling, they have something, they have reverse current. They have reverse current, something like this. It has reverse current. They also have some charge. Okay, so it has this loop current similar to is similar to H. Okay, this is similar to E. This is magnetic dipole and the electric dipole, also similar to microwave. Okay, you can see here is the picture. Okay, the H field is along here is important. Along here, you give an H field, you can see the current. This displacement is similar to necessarily produce some current. This is reverse to H. You can see this current produce H field reverse to H. Okay, so this is can be a negative mu. Okay, this is diamagnetic. Okay, this is out of phase. You can see this loop current. They produce H the reverse to an incident field. Okay, so this is for the mu small and there. Emission cell there you can see means for electrical dipole. Okay, but you know for metal material emission is small and there. Okay, this is metal. So, but this experiment is not very successful. You can see very small region. Okay, very bad. They kind of cheap. But this first experiment is cheap. Okay, this negative N. Okay, for this. Okay. So this is a standard structure used in the optical regime. Okay, I think the most famous one is the fishnet. Fishnet. You can see the fishnet. Fishnet is similar to a, the previous structure is a two parallel nano rod, right? Two parallel nano rod. If I flip this nano rod, I do isotropic. You can see this. Okay. I mean this is a horizontal one. This is similar to parallel nano rod. Okay. This another horizontal pair also similar to a nano rod. Pull them together. This is a fishnet structure. Another is just use split ring. You can see this isotropic. The other claim that they can be fabricated. I don't know how to fabricate this. It's so complicated. With 3D structure, you can see the orientation just isotropic. They use split ring. But it's okay. They use split. They also can use something called a cubic symmetric structure. This can be fabricated with laser writing. They call laser writing. They can fabricate this. Or use a coaxial. Okay, this is standard structure in optical regime. I think maybe most easy one is similar to this structure. I'm not sure which one can be fabricated. This 3D structure is very difficult. Maybe this fishnet and coaxial is easier to fabricate. Easier to fabricate. Okay. Now we talk about some very important concept. Is called a perfect length. Okay. This is a very important concept. The perfect length. Okay. I think in my previous lecture I talked about the the image for Hertzian dipole, right? So give a Hertzian dipole, right? Because due to the Green's function, the E field K equal to is minus j omega mu E minus j k r 4 pi r, then theta theta plus phi phi dot j E j k r prime j r prime d r prime. You learned this before, right? Okay, this is they said that in near field and the far field is a Fourier transform. Okay, it's a Fourier transform, but also a low pass Fourier transform because this k is kx plus ky square plus kz square. It should be smaller than the k square. Okay. Should I draw this figure? I draw the figure many times. The kx, ky. Okay. In the far field, we only can capture information within the sphere, right? Within the sphere, we lose the information out of the sphere. Okay. So this is a key. This is for far field. So for ideal Hertzian dipole, if I use 1D, a bit easier. Use 1D Fourier transform. Okay, I do this one. Okay, this delta function, k space, all the k space. This is x. Okay, so here we only capture the information or in the far field. I do the 1D inverse Fourier transform. I get something. This is nothing but a point spectral function. Okay, this delta function, this delta source. That means we cannot get a perfect point source if I use far field information and do some image. This is a problem, a big problem for resolution. They also call it a diffraction limit. So this is for the image. This is because evanescent you lose evanescent wave information at the far field. This is important. Okay, I give the talk in my previous lecture. Now, metamaterial can solve this partially. I only can say partially, but they can solve this. They can make a perfect lens. What's the meaning of perfect lens? Okay, so they give a metamaterial slab. This epsilon equal to -1, the mu equal to -1. This is air. Okay. Okay. If I put this dipole in here, they have two parts. Okay. First thing, we know that epsilon metamaterial plus epsilon 0 equal to 0, right? Epsilon mu metamaterial mu metamaterial plus mu 0 is 0. This is a surface plasma resonance. This is important. Okay. Okay. This is air, right? But you learn this, right? Epsilon m plus epsilon 0 equals to 0. Okay. This is a surface plasma resonance. Okay. Mu similar. Mu similar. According to the reciprocal theorem, mu similar. This mu m, mu 0 is resonance. Okay, if I have a resonance, they has a very interesting feature called evanescent wave amplification. Okay, it's evanescent wave amplification. What's the meaning of that? Okay, so this is a meta mu equal to 1, so 1 equals to -1. Okay, if it has dipole here, the wave will decay, right? Decay. But they will amplify here. then decay here. Okay. So they will amplify. Go through this resonance. It will decay, amplify, and decay. Put them together, they have same amplitude. We call it evanescent wave amplification. Okay. The condition is here. This point cannot be too far. Okay. If it's too far, it cannot be have this. The distance has a constraint. I talk about this again. Okay. Distance cannot be too far. They call it evanescent wave amplification. This evanescent wave amplification is just due to a surface plasma resonance. Okay. Okay. Here I assume that this is a lossless medium, no any loss. So it's a perfect resonance. A perfect resonance. This is a fourth thing. Okay. This is one important thing. We call evanescent wave amplification. They not decay. Okay. In far field, some evanescent wave will decay go to zero. We cannot capture. But here. Before it goes to zero, it made this interface. They had resonance. They had the contracted interference. They had contour interface. It has amplification. Okay, so they can recover this evanescent wave information. They do not decay this evanescent wave. They primarily call that evanescent wave amplification. Another is for propagation wave. It has a phase conjugator concept. Or compensator. Okay, we'll call it compensator. Okay. This is evanescent wave part. This is evanescent wave. Evanescent. Okay. They do not decay because due to the plasmonic resonance. Okay. Or due to a surface plasma resonance. So how about the propagation part? The propagation part of this is dipole. Okay. Here. What happened? Good. What happened? Right? Okay. This is this is the metamaterial, right? Remember, the diffraction wave does not allow this, but allow here, right? They at the same side, okay? Because n is negative. So from here, this is n equal to -1. The n equal to -1. The n equal to 1. So it's 45 degree. 45 degree, right? So this distance equal to this, right? Okay. So go here, go here. So the total length from here to here is just 2D. This is important. What's the length? If this is D, how about this? 2D. Right? Because it's 45 degree. Here equal to this length equal to this is 45 degree. Because n equal to -1, n equal to 1. Right? It's 45 degree. Okay, another thing important. Along here is air, the phase will delay, right? How about this? Phase will advance, right? Because K along here, right? Remember the K is left-handed will advance. They cancel, and phase advance and phase delay. So this phase and this phase are same. We call it phase compensator, right? So another example of phase compensator is by the indicator, the highlight such. This is PEC. This is PEC. Okay. If this is n equal to -1, I mean epsilon equal to -1, mu equal to -1. Here is n equal to 1, and mu equal to 1, n equal to 1. So how to make a resonator? They can make this arbitrarily small. Okay. This D1, this D2. The only condition is just D1 equal to D2. No half wavelength limit. Okay. For PEC, everyone knows if it is air, half wavelength, right? Half wavelength number is a minimum. So if air is air, so here is lambda is half of the lambda limit. Okay, this is minimum resonance. Here, if I fill with left-handed material with right-handed material, because this n equal to -1, the phase will is advanced. The field will delay. They will cancel them each other. Okay, I go through the previous picture. I draw. You can see here. Okay. The energy will along this direction, but the K along that direction. Okay, so the K is reversed to this group with energy direction, so the K is along this direction, similar to that. Okay, so along this pattern, okay, this phase from here, if I give the wave from here to here, this no phase delay, right? Because it's phase advance and phase delay, they cancel them each other. Okay, because the key is different. Okay, everyone knows that n is different, the k is different, so the k direction is different. You cancel them out, so they can make this as same as positive. Okay, so the only condition is dy equal to d2. They can make same as positive because it's phase advance and phase delay. Because the k is different, n because n is the reverse each other. Okay, so here is them. Okay, now go to air layer, the phase will delay. Now go to metamaterial, phase will advance, cancel. Okay, in phase. Now phase advance, phase delay, cancel. Okay, so here and here in phase. Okay, and the total distance should be equal to 2d. Okay, so the condition, the point cannot be far from. If far from here, at most it's d, right? Because they focus here, right? If I go to here, this D, 2D, I focus here, right? If I go to here, they cannot focus. Okay, okay. So this they cannot be far from. Here also same thing. If ionism is too far, it will decay over. It cannot. So this dipole or this something you want to image, it should be close to this metamaterial layer. This is a constraint. Another thing just lost. I talk about later. So there's a perfect lens condition. The object should be placed into a near field on one side of the lens. Near field is very important. You're very far, they cannot focus. Okay, they cannot focus. They cannot amplify the evanescent wave because evanescent wave has decay over. They also cannot, focus on propagation wave at a 2D direction. This 2D is D. Okay, a synthesis. Okay. Another ohmic loss or slab is 0. No any ohmic loss. If those two conditions satisfy simultaneously, it's perfect. That means a dipole here is a perfect dipole. They can see a perfect dipole here. Okay, no any loss. This is by the country. This is from PIL. Okay, it's a very high impact work. Many people do this work. Okay, so it's perfect lens. How about experimental realization? You can see some experimental result. Maybe by the Zhang Xiang group. I cannot remember, but it's very successful case. Okay. So for optic regime, the thickness D is much smaller than 0. Okay, much smaller than wavelength. That means the thickness D is much smaller than the wavelength. So we got this electrostatic limit is approximated as the electrostatic field. Okay. So there's no constraint for mu. Okay, so mu can be relaxed. It's constraint. Only Epsilon small and 0 is good enough, okay, for electrostatic. You can verify, okay. I did not have to verify, but I believe it's right, okay. However, due to attenuation, in metal they have attenuation, they have some ohmic loss. The resolution, is not perfect because they get lost due to image process, due to this loss. Okay, this is the situation. Okay, so say again, for optic regime, we do not necessarily mu and epsilon small and 0 simultaneously. Why? Because the thickness is very small. We can see the electrostatic physics. Okay, we only have epsilon small and 0 is good enough. Okay, but the problem is loss. Okay, so this loss also, lose some evanescent wave information. This is the case. You can see this is a cause. Okay, this is a pattern. Okay, they use some chrome. Okay, they do some pattern here. This is spacer. It's organic spacer. Because I said the spacer thickness, you can see, 40 nanometer, important. 40 nanometer. How about thickness of layer? Silver, I remember it's 100. Sorry, I did not copy it. Okay, this is 40 nanometer. Okay, so it's very near from silver. Okay, this is important. 40 nanometer. It has spacer. Okay, this is AG. This is for the for amplified ambulance away. It's for silver. This is a photoresistor. This is imaging layer for photoresistor. Okay. You can see this is a picture. This is original AFM picture for this. They just do a cheap imaging here. You can see this is later. But B and C are different. Okay. C is without the silver layer. They just use PMMA. Just use all PMMA. You can see this here. And the B, you can see the resolution is better. Okay, they put a silver. They put silver here. It's B. B is a silver layer. Okay, you can see this is similar to a dipole resolution. This is without the silver lens. You can see it's a red curve. This is with the silver lens. You can see this is a blue curve. Okay. So this is for the ideal dipole. Okay. So they download spread. You know point spread function, right? Point spread function. When you lose evidence wave, it will spread. Okay, they can spread very small. Okay. This is the first derivation. It's a very successful derivation. It uses perfect lens concept. But it's not perfect because loss. Okay. So no perfect lens until now. Okay, because loss. Okay. But maybe some people also have new idea. They put some gain material in silver. Put some gain material in silver to cancel this loss. Now it's very hot topic. Solid plasma has very large loss. I put some gain material to cancel this loss or reduce its loss to make this image perfect. Okay. It's also very hot topic. Okay. So this is a very successful application for the perfect lens. Or even in microwave, someone also do some experiment. But the problem is that you must put this very close, right? Very close to this. Put this later. Okay, so I finished all for the plasma part. Any question about this part? Okay, if you have no question, I can move to the spontaneous emission and LED. Any question about this perfect lens? Okay, no, I just move to the. This is by because we still assignment and the spontaneous emission and the light emitting diode chapter. So I like to discuss this part first. Then final in last two lectures I talk about this characterization and fabrication. Because I have no little. I only know little about the fabrication and the characterization because I'm a pure theorist. Okay, I have no any impairments in handle any device. Okay. So you know my strengths. I only mention about a little bit some principles. So I like to talk about the last chapter first about spontaneous emission, light emitting diode, because you have two assignments in this chapter. So let me go. So call about spontaneous emission. Spontaneous emission and so I think some content you are familiar. Okay, this part I think is the most difficult part in my lecture. Okay. Okay, this is the most difficult part. It is especially for 4, 5, 6. It's very, very difficult. I don't think you can fully deeply understand 4, 5, 6, but I want you to know something about this. Because why this chapter is too difficult? Because until now, I only talk about the classical Maxwell equation. Even nano optics is maybe 30, 50 years. It's relatively young. But all the theory framework are based on the classical Maxwell equation. Okay, this is very important. All the theory are based on classical Maxwell equation. But this chapter are some content are beyond the classical Maxwell equation. I talk about some quantum electrodynamics. So this part is very difficult. For quantum electrodynamics, Maxwell equation, why it was invented by or summarized by the Maxwell equation is 150 years ago. 150 years ago. Okay, so you learn something very old, 150 years ago from Maxwell equation. Okay. But for quantum electrodynamics, only 50 years ago. Only 50 years ago. So I talk about this 5 or 4, 50 years ago. Okay, so it's very young, still very young. Okay, some researcher in here study spontaneous emission. Maybe some study called radial oscillation or strong coupling. This is fully a quantum electrodynamic framework. Okay. So I like talk about this, show some basic idea to you. So this lecture I only talk about 1, 2, maybe 3, 1, 2. Okay, this is classical. Oh, maybe in next lecture I talk about 4, 5, 6. This is fully quantum mechanical. With we will show some spontaneous stimulate and absorption picture. I believe most of you will learn this picture in undergraduate course. I assume that you will learn this spontaneous stimulate emission and absorption in undergraduate course. Okay. For spontaneous emission is a process. Some atom, molecule, or quantum dot. We call it a quantum system. Okay. It's an atom, molecule, or quantum dot in an excited state. Okay. Some atom in an excited state. Then they then they have a transition from the excited state to ground state, to lower state or some ground state. Then emit a photon. Okay, emit a photon. It's called spontaneous emission. And this photon, the phase, random. This is a fully random process. They emit a photon in every direction. Okay, every direction. Okay, and the polarization and no polarization. Okay, typically no polarization. Every direction. They are fully random process. But it's very important. They have many applications. Okay, like a fluorescence tube. Okay, you'll see some all the light bulb. You can see this is a spontaneous emission because you can see that there's many rays from this. This is okay. They emit every direction randomly, not coherence. Okay. The wave, the light, not coherence. Okay, this is called spontaneous emission. This is a very important application. Maybe someone still use this. Okay. This is an important application. The fluorescence tube. Another is just I think a laser and LED has an important application. What's the meaning of LED? So LED is just spontaneous emission. Okay, LED is just spontaneous emission by the relative recombination electron and holes in the active region of the diode on the forward bias. Okay, they add a bias. Okay, add a forward bias. So electron and hole can form a 2 electrons that move because of the driven force to add a bias. They can move to active region. When they combine, they emit light. This light is spontaneous emission because they have no phase are very random and direction typically are very random. Okay, this is spontaneous emission. And for laser start from spontaneous emission and then operate at the stimulated emission regime. That means if I want to laser become laser, first it was spontaneous emission, then they can go to stimulated emission. If you can enhance the spontaneous emission rate, you can reduce the threshold current of a laser. Okay, that means they can use very few power. The laser can be leading. Okay, so this is important also for laser. Although laser it operates at a stimulated regime, first they study from the spontaneous emission. So this is a spontaneous emission. I like go to another is quite different is stimulated emission. For stimulated emission, okay, you can see they have incident photon. It's important. We know incident photon here. can see no incident photon. It has incident photon. One incident photon, okay, to be illuminated as an atom. Okay, the atom they have some they have some atom, they have some electrons, so it's located at the excited state. Then they will jump from excited state to ground state. They interact with this incident photon. Finally, they have two photons. Okay, this emitted photon by this transition has the same phase, direction, frequency, polarization with the incident photon. Okay, this is important. Okay, so that means the emitted photon has same frequency, polarization, direction, frequency with the incident photon. Okay, this process is coherence. Like later you can see later we can propagate in very long distance because it's coherence. A phase, they have the phase, polarization, frequency, direction, and they follow the incident wave. We call it stimulated emission. This is very different from spontaneous emission. This is a random process. They emit incoherent, okay, and non-directional and unpolarized photons. Okay, so this is a basic difference. Another, third part process is just absorption. Okay, just ground state electron absorb the photon energy go to excited state. This absorption is just a reverse process of stimulated emission. Similar to reverse process of stimulated emission. Okay, I believe most of you learn this in undergraduate course. Okay, in stimulate, absorption, and spontaneous. But if my course only teach you something knowledge like this, it's not my style, right? It's too simple, right? I talk about this more deeper one. Okay, about this. Okay, we'll have break. Okay, 5 minutes break. Data balance theory is very important for solar cells and laser LED. I hope everyone can know the detailed balance equation. Okay. So, what was the meaning of detailed balance equation? I talk about later because first I talk about Einstein AB coefficient. It's very famous by Einstein. So Einstein AB coefficient is related to Einstein A coefficient because A is related to a spontaneous emission. Okay, so this is spontaneous emission. Called Einstein A coefficient. Another related to absorption and stimulation emission called Einstein B coefficient. Okay, this is a very simple process. Okay, it says the N1, N2 just number. Okay, inside atom at two different states. Okay, N1, N2 just number of atom in the different like ground state and inside state. Okay, so someone also related called Reed equation of dN1 over dt. Okay, I wrote this is spontaneous emission. Spontaneous emission equal to A to 1 equals M2. So this means the increase in the unit time, the increase of the atom density at the ground state. Okay, the increase of atom density at the ground state just proportional to the total number, total atom density at the excited state, and there's some coefficient. This is very simple. This is just Reed equation. Very simple. Everyone can understand this. This is called Einstein A coefficient. Spontaneous emission. Einstein B that has a stimulated emission. First. This is stimulated emission to 1. Okay, here. This is stimulated emission equal to B to 1. Okay, from 2 to 1. N2 rho V. Okay, here you can see it has this. This is important. Why? Why no rho? Because no rho in here. You have no incident wave, right? You have no incident wave for spontaneous emission, right? So the increase at its ground state, the increase or number of atoms at the ground state is just proportional to the number of the atom at the excited state. Okay, because no incident photon. No incident photon. Here, okay, similar, there has another coefficient called B, we call it S and B coefficient. Okay, the N2, every time is very similar, but it has a rho here. Okay, rho is just antigen density, just a spectral antigen density. I mean, it's antigen per unit volume per unit frequency of the isotropic radiation field. Okay, we call it rho V. So because they have incident photon, so it has rho V. Okay, this stimulate emission. Another is absorption. Absorption just go up. Like go here. This is H bar. E2 1. This is D N 1. Okay, this is D N 1. It's dN1 over dt because they will lose some atom, lose some electron. E1, 2, N1, and the rho V. So they have rho V. Okay. You can see they have a minus here. Okay, the minus means they lose. It means a decrease over this atom number at ground state is proportional to the number of N1, this layer, and the light and the radiation antigen density, rho V. So the rho V I'll talk about later how to calculate the rho V. How to calculate rho V. The rho V is related to the black body radiation. This is a picture. This is a real equation. This is for absorption. This is it's easy to understand because it will decrease because it's a minus. It decreases from the ground state, so it's N1. So what's the detailed balance equation? What's the meaning of detailed balance equation? So you know at that time they had a history. They had an interesting history, you know. Because before the spontaneous emission, people only know the stimulated emission and the absorption process. They only know these two processes. They are not aware that spontaneous emission exists. Okay, they only know this. But they found that, okay, they can verify. Typically B1, 2 equal to B21. You can verify later, okay, talk about it later. Okay. You can verify. But people know that the N1 and N2 typically are not equal to each other. According to our statistical reason. That means, everyone knows the atom has a larger probability located at the ground state, right? And a smaller probability located at the inside state. So N1 and N2 are not balanced. You know, N1 and N2 are not balanced. So this cannot balance, so people find the spontaneous emission should exist. This is the way to find spontaneous emission because these two processes cannot balance each other. Because N1 cannot balance N2. So the detailed balance theory just show these three processes to be balanced. They balance in the microscopic level. Okay, we call detailed balance. Not the detailed balancing or detailed balance equation. It means the two at a thermal equilibrium. Okay, at a thermal equilibrium, the three processes should be balanced. Okay. A21 and 2 plus B21 and 2 rho V minus B12 and 1 rho V equals 0. This is detailed balance equation. Right. Oh. We go to this slides, which see what happened. We see the N1. Okay, we see the ground state. Okay, we see the ground state. They had three processes. Okay, one process called spontaneous emission. They will increase, right? Increase the ground state atom number. Okay. Stimulated emission also increase the number of ground state. okay, but the absorption will decrease the number of atoms at the ground state. So 3 added together, the net, it should be 0, equal to 0. It said no increase or no decrease at its ground state, at a thermal equilibrium. This is important. Everyone knows this. What's the meaning of thermal equilibrium? You know, for a device at a PN junction, you know, if for PN junction, you pull them together, okay, like a water. This water is higher, this water is lower. They has a connection. If I remove this connection, they make this balance. This balance is called a Fermi level, similar to Fermi level. Like a PN junction. A P type, they has a Fermi level is lower. The N type has Fermi level higher, right? They pull them together, the Fermi level align. They call it thermal equilibrium. What's a thermal? How to break the equilibrium? They have 2 ways to break. One, you add a bias. If you add a bias, you break the thermal equilibrium. You add a voltage to this, like some circuit or laser, you add a bias, it does not thermal equilibrium. Okay. Another use sunlight to illuminate, like a solar cell. It also break the thermal equilibrium. That means they have does not align Fermi level. Okay. Like so they call it quality Fermi level. Like if not thermal equilibrium. Okay. So this is important concept for thermal equilibrium. For thermal equilibrium, the net atom number at the ground state should be 0. No increase or no decrease. Okay. Net increase should be 0. I mean no increase or no decrease. So add them together, it should be equal to 0. This is called a detailed balance. It's only valid at an equilibrium state. Okay. So remember, non-equilibrium. I know. Right. What's non-equilibrium? There are 2 ways. Add applied bias. Another use sunlight. You can break this equilibrium. And the Fermi level, EFN, are not equal to EFP. Okay. That means for PN junction, okay, for PN junction, the Fermi level does not align. Okay, does not align. They call it this is non-equilibrium. Equilibrium, the Fermi level should be aligned, like a water. Okay, equilibrium. Okay. Thermal equilibrium. This is a detailed balance. So that means emission and absorption are balanced. Okay, this is emission and absorption are balanced. This is a very famous black body radiation law. Okay, what's the emission and absorption balance? Consider a black body. Okay, this is a black body. Typically, this model, okay, it only has a small hole. A rays go. There's a total reflected, no absorption. Okay, and they go out. What's the black body? Black body is the emission equal to absorption. They are at a thermal equilibrium. Okay. First thing, a gold emitter is gold absorber. Okay. First, it's the black body. Okay. They absorb the EM energy very broadbandly. Okay. They absorb the energy. They produce, thermal. They increase the temperature. They increase. If you absorb something, increase temperature, right? Increase temperature. Okay. Well, increase temperature, you emit EM wave like infrared out. So this emission should be balanced. The absorption. Okay. So a gold emitter is a gold absorber. This is for the black body radiation law. Okay. The gold emitter is a gold absorber. Okay. So this is a very important concept. Okay. The gold emitter is gold absorber. And they absorb the electromagnetic energy. Okay. They increase the temperature. Like our body, that will release EM wave. Like people will release infrared, right? They can use the infrared detector to see us. Okay. Then this emission will be balanced with absorption. Okay. To make this temperature constant, like okay, to make it constant, it's very simple. We call it equilibrium. Okay. So this black body this is the ideal model. So black body radiation, just electromagnetic radiation in a thermal equilibrium. It's very important. Yeah, thermal equilibrium. Okay, thermodynamic equilibrium state with environment. When you heat up right? When you heat up your sample, it's not thermal equilibrium. Okay. You pour something, do not disturb them. Okay. Like you can see a very black, maybe very black environment in vacuum, right? Do not disturb them. This is thermal equilibrium with the environment. The temperature become constant. Okay. So this is called thermal equilibrium. It's a uniform temperature distribution, constant and a uniform temperature. Okay.
And you mentioned about the water.
Water. Okay.
For example, the water is flowing.
Yeah.
Is it equilibrium?
Yeah. Initially, similar to p-n junction, p-type and n-type, they have different Fermi level because the electron density are different. When you touch them, put them together, similar, I remove the pin hole over these two water. The magnet water, this go down and go up. Then thermal equilibrium. And don't disturb them. Okay, just touch, don't disturb them. Don't add bias, don't use sunlight to shine them. This is everything in a dark, okay, in a vacuum. So this is thermal equilibrium. Okay, this is an important concept. It means the object and the environment, they are balanced, okay, each other because thermal equilibrium. Okay. This is a very important concept. Okay. So the radiation has specific spectral and intensity, depend only on the temperature of the body. Okay, this is interesting. Black body radiation said the emission spectrum only depend on the temperature. This is very important concept. Only depend on temperature. It's black body spectrum. Okay, you can see that this is the black body radiation line. This line is sun, our sun. We can see sun black body. It's a 60,000 K. Maybe more accurate is 5,800 K. Okay, for sun, very high temperature. You can see this is the sun. So this is really we see the visible light. Okay, we see the visible light because this is a peak. You know, the sunlight, the sun has a temperature here. They have the peak. You know, emission and visible light. So we see the sun. So you can see everything are not so scientific. Everything are so magic. You see the sun because this temperature here. You see the visible light regime. Okay. Okay. But this is different regime. You can see. How about the room temperature? 300 K, right? 10 mu, right? 10 micron. Okay. So for room temperature, the emission is 10 micron. It's infrared. Okay. Typically our body, okay, you should use infrared to see that. You cannot see with your eyes. Right? You cannot see the temperature with your eyes. Okay, because there's a peak at the 10 micron meters. Okay, you can see different temperature has different peak. They will shift from the higher to lower shift. You can see shift. This is a basic black body radiation spectrum.
Can sun be considered as a black body?
Huh?
Sun.
Can be seen. Can be seen approximately the spectral line of this black body radiation. But sun typically cannot be rigorously black body because it has many chemical reaction in the sun. But the spectral line it can be used for approximation. It's interesting. So as most energy release infrared. Okay, so we cannot see in our eye. This is the reason. So everyone know what's the physical origin of the Johnson noise or dark current? Johnson noise or dark current. Okay, this is released for black body radiation rod. Like we know every device has noise, right? They have noise and noise. This noise is related to this temperature. Okay, because every device like every absorber, like resistance. Resistance is a good absorber, right? It has box, right? Every absorber will emit electromagnetic energy, right? They also receive electromagnetic to keep this temperature constant. Okay. So at a thermal equilibrium, the resistance they has current fluctuate in the body. This is noise. Okay. So this temperature also, I will talk about later, it has a related to this noise issue. We call this black body radiation. And how to get this spectral line? How to get this spectral line? This is how to draw this spectral line. What's the stereotypical? Okay, and talk about this. This part I think is a little bit difficult. So a procedure to finding the energy density spectrum, okay, of the radiation. it has two parts. It has two tasks. One, to find the number of allowed mode per unit volume per unit frequency. Okay. They find the number of allowed mode per unit volume per unit frequency. Okay. You learn this concept called density of state, right? Density of state is just number of mode between omega and omega plus d omega. Right. Here I add a per unit volume. Okay. It's similar to local density of state concept. I talk about this later. Another is to find the mean energy of each mode. Okay, so I have two steps. Find how many allowed mode per unit frequency per unit energy. Okay, per unit frequency per unit volume. Then calculate the average energy from each mode. Multiply them together, it's just black body, right? We know the number of mode. We know the average energy from each mode. We multiply them together. We get this black body radiation. This is from Seng Liang's book. You can, this part I have no any textbook, This is relatively young. I just copy different sources in my research. So they have two tasks. One, allowed mode. For frequency, for volume. Okay. Allowing mode for frequency, for volume. I consider a cavity. Black body you can see a cavity. Consider a cavity. With a dimension maybe A, B, D, something like this. This is a cavity. Everyone knows for 1D cavity. Give a 1D cavity. Its length is A. How about its resonance? Okay. Resonance frequency or resonance wavelength. The resonance wavelength, the A, 1A equal to half wavelength N. Maybe L, use L. L equal to 1, 2, 3. They become a resonance, right? Right. When the length of this 1D cavity equal to the integer number over half wavelength, it becomes a resonance. Okay, it's no problem. So I get this lambda equal to 2A over L and V and F. Physicists like use V. I don't know why, but they use V and F equal to C over lambda, then equal to mu per C 1 L over A. Right, this is for 1D. For 1D. This is for frequency. Resonance frequency. This is for 3D. 3D. This is in frequency space. It has fx, fy, fz. No. Each point like a mode. Each mode represents each mode. Okay. This. For small volume, each mode I ask you in this volume how many mode can fill in this volume. How many mode can fill in this volume? Okay, how to calculate this? First thing, you should calculate this resonance frequency. Okay, this is resonance frequency. Okay, here, this is resonance. It's a V square. This is x direction, y direction, and z direction. It's not. It's right. Yeah, it's right. It's right. So this is how many modes? You can see in a quarter hemisphere shell. I mean, I only consider hx or vx, vy, vz larger than 0. So this is just 1 over 8 sphere. It's a 1 over 8 sphere. One sphere I will cut. I will 6. And thickness of dv. Okay, has thickness of dV and the radius of V. The radius of V. Okay. So the number of moles contained in the shell, I just use this unit. This 8 over 8 because they only consider Nx, Ny, and Az less than 0. Okay. Then 4 pi r squared dV. Okay. This is a total volume. Okay. Okay. And here. This is, you can see. How about the how about the small volume? I mean, they has a cavity frequent domain. I did not use the field. I use this better. It's Vx, it's Vy, it's Vz. There's many small volume. This is one mode volume. You can see. Then this total volume, then I over this small volume for one mode. This size is just 2A over 2A. This size is just 1 is the frequency, right? Frequency just one over square mu epsilon 1 over 2A multiplied. This small volume just 1 mu epsilon 1 over 2A 1 over mu epsilon 1 over 2B multiply 1 over mu epsilon 1 over 2C. This is the dimension. You can see here, I said each point has each mode. How about its distance along z direction? How about its distance? Yeah. It's just just resonance frequency. I derive that. You can see, I assume that the lambda, the A equal to integer number of half lambda. Right, integer number of half lambda. The L equal to 1, 2, 3. So I get is lambda equal to 2A over L. The F, just the frequency equal to something like this. Okay, something like this. So L equal to 1, 2, 3. So you know distance between each mode just 1 over epsilon over 2A. Okay, 1 over epsilon 2A. Okay, so this volume for this small mode volume just 1 over because epsilon 1 over 2A, 1 over 2B, 1 over 2C. So this is the total volume. Sorry, this is the total volume, right? 4 pi V square, 4 pi R square dr over 8 because I only consider positive region. I over a small volume of this cavity. Okay, this is small volume. Okay, just okay. 8 V mu epsilon 3 over 4. Okay, something like this. Then multiply the T and TM. Okay, and 2 polarization. This is. So everyone see that this volume. I cannot draw this in. That means it has a length, height, width. It has a small mode volume. This volume just 8V mu epsilon 3 over 2. Just something I wrote. I hope everyone can know this how to tackle this guy volume. It's something like this. Okay, it's small volume. I mean it has a large volume. This is a small volume. I calculate this the total total volume, over this small volume, I can get this number of mole. Okay, this is small volume size. Okay, this is very easy to get by this. You can see. Okay. Because the lambda, the A equal to half wavelength, initial number of half wavelengths. So F is just some C equal to L over 2A. So distance of each mode is C over 2A. Okay, this is this. So this part just it's just mode volume for each mode. Okay, this mode volume for each mode. This part has a total volume for this called hemi shell, because they have dB here. I mean they have another shell with a dB. Okay, it's called hemi shell. Because we want to get this allowed in mode per unit volume, per unit frequency to have dB here. Okay, there is two different directions, T and TL. Okay, I pull them together. This is for V. Okay, this is just the resonance frequency for the cavity. Just the resonance frequency for the cavity. You learn this basic electromagnetic theory. I pull them together. Okay, I get this LDOS. LDOS is 8 pi V squared over C squared. This is C, right? C is cube. Because it's a unit volume per unit frequency. So I ignore V and dB part. So this is local decibel state. So it's easy to verify. The number allowed in mode per unit volume per unit frequency. So the basic idea I say again. First, you should represent the total volume for this quarter hemisphere shell. Okay, this 8 here because they only have to consider Vx, Vy, Vz larger than 0. Okay, so this 8. The 4 pi r squared, this dV, this is just normal integral integrand for spherical system. Okay, this is the first part. Okay, it's the total volume for this quarter hemisphere. Then I over the volume of the small mode volume for each. Okay, this small mode volume. It has a a size with 1 over 2d, 1 over 2dc, 1 over 2ac, and 1 over 2bc. Okay, this is for a small box. It's small box. It's volume for a small box. I over the small box. I told about they have two different polarization. I get this. Okay, the number of modes per unit volume per unit frequency. This is a local density state. It's called local density state.
So this is a validated field.
Yeah, no. This is a free vacuum, free vacuum. No any information necessary. This is an also this is every mode are related. No evidence. Okay, this is the first. We complete the first task. Okay, so this is the first task. I hope everyone can understand. I draw this. This is V mode. So 4 pi V squared dV over 8 over V mode. Just have to divide local density state. Then I draw this. I use another thing. I call this Q. This Q. And the V here is just V squared just for this cavity. Resonance cavity, resonance frequency. You can verify this. You learn this in the basic electromagnetic theory. This is so you can get this density state. Another thing, how to get this average mean or average energy for each mode. Previously we get the number of mode. Okay, number of mode per unit volume per unit frequency. Here I want to get the for each mode for this average energy for each mode. Average energy for each mode. This is a fully quantum mechanics. Okay. I teach you this statistic for photon and electrons. For photon, any photons can occupy allowing mode or any allowing mode or state. Okay. I told you that for electron, right? It has state. It has some state, right? So you add an electron, you occupy state. Another electron should occupy different state. Another electron should occupy different state. This is called a Pauli exclusion principle. This is for electron. Right? I talk about this. And for photon, it has a different side. I add a photon. Okay, I use this. Right? The first photon occupies state. When you add another photon, they also can occupy the same state. Right? No problem. Third photon occupies. Maybe the third photon they can occupy another state. This is quite different. For electron, two electrons cannot occupy the same state. They call it Pauli exclusion principle. A photon, they can occupy any state. Okay. So that means for each mole or any mole, they can be many photons. Can be 1 photon, 2 photons, 3 photons. You don't know which photon, how many photons in each mole. Okay. This is the basic of physics. This is the picture. This is a 0 photon, 1 photon, 2 photons, 3 photons, 9 photons. Okay, in each state. In every state, you don't know the number of the photon number. I said because any number of photons can occupy any allowing mode. This is statistics. Okay. So for each mode, you don't know how many photons in this mode. Maybe 1 photon, maybe 2 photons, maybe 3 photons. You don't know. But you know that the probability satisfies the Maxwell-Boltzmann distribution. Okay, that means if you have a high number, photon number, it has a small probability. Okay, has small. It's E minus E over kBt. The E here is just here. That means if the photon number is too much, the probability is very small. Okay, this is some normalized concept. Okay, this is called Maxwell-Boltzmann distribution. Right. So 0 photon or 1 photon, they have larger probability, right? They have many photons, has a very small probability. Okay, for each mole. Okay. That means for given each electromagnetic mole, you have possible have 1 photon, 2 photons, 3 photons. You don't know, but you know the probability. Okay, 1 photon probability or 0 photon should be larger than 3 or 5 photons. Okay, because it's exponential decay. This is the Maxwell-Boltzmann distribution. This can be derived, but it's too complicated. I don't talk about deriving it. Okay, then how to get everything energy in a mole? Okay, this is a very technical. N h bar omega. HV just h bar omega. Okay, HV just h bar omega. H is Planck constant. H bar is reduced Planck constant. H bar omega just 1 photon energy. H bar omega just 1 photon energy. H bar is constant. NH bar omega or NHV just a photon energy for n photons. Okay, this is the probability distribution. Okay, this is a normalized concept. Okay, so you can see this equation. This is energy. NHV is a photon energy for n photons. Okay, NH bar is for n photons. Well, these n photons has a probability here. I summation together over this normalized constant. Finally, I get this. HV, EHV over kBt minus 1. The key here is a Boltzmann constant. Typically with KB, we call Boltzmann constant. Boltzmann constant. Any question about this? This is very important.
Should the Boltzmann summation equal to 1?
This is not equal to 1. It's a normalized constant. It's not a normalized constant. I don't think this is equal to 1. But it should be normalized to this. They can make this. How to say? You should make this is a probability distribution. That means they go from 0 infinity go to the p should be go to the 1. Right. So they normalize with this. Okay. Normalize with this. Okay. So let me clarify again. For each mode, for each mode, you don't know how many photons, okay? Because both aesthetics don't know how many photons. But you know, if we have a few photons, we have a larger probability, okay? So how to get this average energy? We just use this, okay? This is a photon energy. If we have n photons, the energy is nhv. Okay, I multiply this probability and over some normalized constant, add them together, finally I get this average energy. Okay. This is average energy. This is for each photon. So you can see, interesting that the average energy for each photon with a frequency v is just hv equal to something like this. This is called average photon number. Okay, you can split. This is hv. This is photon number. Average photon number. Another, I want to see, you want to see that if v is very small, what happens? If v very small, E hv over kBt minus 1 equal to what? If v is very small. Just hv over kBt, right? Just hv over kBt. Yeah. hv over kBt, hv over kBt equals what? kBt. Everyone knows kBt. Right? kBt just energy for each mode, right? Remember in classical, kBt, like ideal gas, is kB over T, right? If you give a temperature, how to the average energy for this ideal gas is kBt, right? You can see, if V is very small, just kBt. Okay, so this equation is quantum mechanics. They can be available for the classical, also can be beyond the classical. Okay, you can see this is kBt. So this is, so put them together, the radiation energy per unit frequency per unit volume equal to the number of mole. Okay, it's number of mole multiply the average energy for each mole. Multiply together. This is just a black body radiation law. Just I draw this curve. Okay, you can convert this or convert to intensity. So it's not easy, right? So this is curve. This curve is just I just derived this curve. Right? There's a two part. Okay. This black body radiation. You can learn this again. Okay. When I first time I learned this, I totally confused all the concepts. That is very important. Okay, very important.
So it's for general black body. It's valid for all black body.
All black. If this black body is all, this is very universal. It's very useful. Even in solar cell, we use this equation to calculate something. Calculate dark current. Okay, like theta band theory. So, the history. The history. In the history, I remember someone derived some equation. In history, they call it a catastrophe disaster. You remember this catastrophe disaster? At that time, they did not derive black body something like this. They derived black body relation from something like that. Go to infinity. Okay, it goes to infinity. That means at a short wavelength, it has the infinite power. Classically, if you do not use this statistics, here. If you only get kBt, you get this solution. You get this solution for the intensity. Okay, just go to infinity. Okay, at that time. So people just said, oh, classical physics has some problem. This is very important. Flat black body. They have three cloudy. Why is it called ultraviolet catastrophe? Just people said, oh, in your classical theory, ultraviolet, you get an infinite intensity. But people said, oh, you open the door, if the door is at black, you open the door, you burn yourself. Okay, you cannot, right? So the people use this theory to correct this. Okay. This is a very important history reading. If you do this equation, you do some approximation when V is HV is smaller than 0, you can get this. We call it Rayleigh-Jeans law. Called Rayleigh-Jeans law. You can use this equation. Okay, I finished this part. Now finally, I have 5 minutes and just conclude this part. This is the final step. This final step. Remember detail band's equation, right? Okay. This is spontaneous emission. This is cumulative emission. This is absorption. They are balanced. I talk about this. How about the rho? Oh, here I derive. Okay, this is the black body relation. Okay, this is a local density state. This is every energy for each mole. Right, put them together. This is rho. I decompose the rho equal to FV into something like this. I put them together. I substitute to the detailed balance theory. Okay, together. Here, how about the N1 and N2? How about N1 and N2? You also use statistics. Okay, N1 and N2 also satisfy some statistics. It also satisfies Maxwell-Boltzmann distribution. Also satisfies Maxwell-Boltzmann distribution. You can see here, the N1 is the ground state, right? N2 is excited state. The distance is h bar v, so you can see smaller. E minus h bar v over kBt, right? E minus h bar v over kBt. You can see here. Why they have the E h bar v over kBt? E h bar v over kBt here. Because the N2. Go to N2. N2, it has an excited state. It has smaller probability. We use Maxwell-Boltzmann distribution. The G1 and G2 here is just some degeneracy. So you can assume it's 1 to no degeneracy. Okay, it has some degeneracy for N1 and N2. It has some degeneracy. Okay, pull them together, do some simplification. You can see this equation. Because they are equal to each other at arbitrary time, arbitrary temperature. Okay, equal to each other. So this part, A21, G2, this part equal to B12, FV. It should be equal to this. And this part, A21, G2 equal to this part. Okay. Because it's arbitrary temperature. So finally you get this equation. B12 equal to B21 equal to G2 and G1. G2, G1 is just degeneracy. If no degeneracy, B1 is equal to B21. This is the reason. Okay. Another, spontaneous emission can be related to a stimulated emission with this concept. This is done by Einstein at that time. Or they then become very famous. It's done by him. It's all the person done by him. Use this balance. They use this balance theory. They use this rule. Rule is by the black body radiation law, Planck's law, I derived previously. The N1 and N2 also use the Maxwell-Boltzmann distribution again, because N2 has an excited state that has smaller probability. They multiply E minus HV over kBt here. Okay. They pull them together, make it equal to each other. You can see this equation. When they equal to each other, this part, H21, G2, exponential part, must equal to B12, G1 exponential part. Okay. And H21, G2, this constant part, must equal to this constant part. Because this equation is right for arbitrary time. Okay. So this is the logic. So finally, you get this equation. Okay, if no degeneracy, absorption A and B coefficient for absorption and stimulated emission are same. If no degeneracy. Okay. And another A and B can connect to this concept. So this is done by the Einstein at that time. Because Einstein, the most contribution, Einstein said the N1 and N2 are not equal to each other. According to the Maxwell-Boltzmann statistics. Because N2, the number of atoms at N2, it should be smaller than the number of at N1 at a thermal equilibrium. So they found that the absorption and the stimulated emission are not balanced. Okay. You can see this equation. If you know this term, N1, N2, if N1 equal to N2, they are balanced, right? N1 equal to N2, because B12 equal to B12. If no generous, you have balance, but N1 equal to N2. Okay. So they found they must add this term to balance. So this is a finding, and this is continuous emission term to balance. So this is a very famous work. I just tell you. You can maybe think about it by yourself. Okay. Well, any question about this part? I finished my lecture. Any question about this part, how to derive this AB coefficient, how to connect them?
Is there an experimental background?
You said this? I think at that time I don't think they have experimental to measure spontaneous emission is very difficult. But black body radiation, they can be verified in experiment.